In this video we're going to take a look at Intergalactic Recovery, which is an easy forensics challenge, and the description says Miyuki's team stores all evidence from important cases in a shared RAID 5 disk. Especially now that case IMW1337 is almost completed, evidences and clues are needed more than ever. Unfortunately for the team, an electromagnetic pulse caused by Draeger's EMP cannon has partially destroyed the disk. Can you help her and the rest of the team recover the content of the failed disk? So this challenge was taken from the recent Cyber Apocalypse CTF, which I didn't get a chance to take much of a look at. So let's take a look at this challenge now. The description's made it pretty clear what we need to do. I've already downloaded the files into a local directory. So we'll start off by doing some basic file checks. Let's check the file types first of all. And we'll see that all three just show as data. So we'll have a look at the file sizes. And we'll get a clear indication of which disk is corrupted, because we've got two here that are the same size, and then we've got one abnormally small disk image. That's fine. Let's also try to grep out, let's go for HackTheBox case insensitive and grep that from all the image files. We can do that with -A just to make sure it shows as strings when it's a binary file. And we will see HackTheBox in here a few times, but it doesn't seem to be in relation to a flag. We could have a look at the strings in general. Let's look for strings greater than 10 in all of the images. And you can just have a look through here to see if there's anything recognizable which could help us make sense of the data. You can see here we've got some directory structure. We've also got a PDF file, imw_1337.pdf, which sounds particularly good. I did actually try immediately when I saw that trying to run like foremost and binwalk on these files to see if we could extract that out, but we can't at the moment. What we'd normally do is open these images up in something like Autopsy or FTK Imager, as we know they're disk images, but that's not going to work for us in this case because of the RAID 5. And if you are going to do that as well, I normally go over to my Windows system because I have the latest version of Autopsy and FTK Imager installed there, although Kali and Parrot do come with Autopsy. It's a really old version, it's like 2 point something, whereas like the current version is like 4.7 or 4.9 or something like that. So I would go onto the GitHub if you want to get Autopsy set up on your Linux system. I would go and install it manually. But even then, there's actually no way to deal with these RAID 5 drives by default. You can look up some commercial solutions which have it built in. I was starting to look at some open source solutions, but then I realized it's not actually that difficult for us to recover it. So let's have a closer look at what RAID is and discuss memory a little bit. So I'm going to bring up an article which I'll leave in the description along with any others that I cover in the video or which I think will be useful. And this is just a primer on computer memory, which I'm not going to go into too much detail. You can do this in your own time if it's something that you need a recap on, but just the important stuff here is that we have volatile and non-volatile memory. So a volatile memory is like our CPU and our RAM, and basically it just means that whenever it's not receiving power, if the computer loses power, if it's switched off, everything that's in the RAM and everything which is in the CPU, in the registers and in the cache will be lost. So that's our volatile memory, and then we have non-volatile or permanent storage memory, so that's our hard disk or CDs, DVDs, things like that. And that doesn't require power, the data is permanently stored. And we have a lot of different categories here as well. So this is in a pyramid here. We can basically think of this as the higher up you are, the faster things are. And the further down we go, the more storage that we have. So you'll typically have a lot of storage in hard drives, and less in RAM, and then even less in the CPU, in the registers, and in the cache. And the speed decreases as we go down this pyramid. But if we talk about hard drives in general, there's quite a lot of options now as well. So we have our hard disk drives, which is a hard drive with an actual spinning disk, as would have been traditionally used. We have SSD, so solid state drives, which don't have a physical spinning disk and are significantly faster. They can also be connected in different formats. So you have SATA, for example, which is quite a fast way of connecting the hard drives, and you have SATA 3 gig and 6 gig and stuff like that. And you also have now NVMe, which, let me just open up a quick article on that as well. So I don't want to get too sidetracked with this. I promise we'll move on in a moment. But as we can see here, NVMe is a communications interface and driver that defines a command set and feature set for PCI Express based solid state disks with the goal of increased and efficient performance and interoperability on a broad range of enterprise and client systems. So we can see a comparison of SATA and PCI Express, the different speeds and how they've evolved through the different generations. And the communication drivers, so NVMe is the new one. We can see it communicates directly with the system CPU rather than with the SATA controller, and here's the various speed differences. And then the form factors as well, so how the drives have got smaller. We can see the SATA drive there at 2.5 inches, and now the M2 chip, the hard disk that I got, it looks like a chip of RAM. In fact, it's actually a lot smaller than the DDR RAM that I have in my computer at the moment, and because of it's connected to this M2 bus, it's significantly faster. So yeah, I'll not go through this in too much detail. I just wanted to mention that. I'll talk a little bit about this in a second because I've got a few different hard drives in my computer, so I'll talk about how I set those up as well, because I do have a RAID config. Okay, so that's that out of the way. Let me open up an article on RAID 5 and we'll talk about that. What you need to know. So let's take a look at this first of all. I'm going to start from the bottom at RAID 1. As we can see here, particularly easy to understand as it mirrors the contents of one hard drive to another, which creates a redundant system. There is no gain in performance by choosing a RAID 1 configuration. So essentially this is like a backup, right? You can have two hard drives. Let's say we've got two hard drives, they're both 100 gig each. You could have two hard drives and they're both mirroring the exact same data. So whenever you store something to the hard disk, it stores it in both locations, and it means you have redundancy. If one of the hard drives fails, you've still got a backup of the rest of the data, and the data could just continue. There'd be no interruption in the service. It would continue to use the working hard drive while you then just have to get the other hard drive replaced. RAID 0, on the other hand, this is a configuration which I have set up between I've got two SSD Pros, Samsung SSD Pros, and they're both the same size and speed and everything like that, which is important. And essentially this will mean that your data is spread across the two disks. So let me actually just read out the explanation. Based on stripping techniques of intersperse data between multiple hard drives to provide increased performance, used on a minimum of two disks, the RAID 0 divides the data into tapes and distributes them on the various available storage units. Since data access is done on multiple disks at the same time, the speed is increased, but the lack of redundancy does not give greater fault tolerance, often preferred by professional gamers who desire speed and performance above all else. So essentially you could have two or more hard drives. You could have two, you could have three, you could have four, and you basically say that I want all of those hard drives to act as a single drive. So on my computer I have two drives in RAID 0, and whenever I open up my computer it just shows those two drives as a single drive. And whenever you store a file, whenever you read or write something, it's reading and writing to or from both of those drives or all three drives at the same time, which of course means things will be faster. So if I want to save, say, a PDF document, if you're able to write half to each drive, obviously you're going to have double the speed, and then whenever you go to read, you'll have double the speed because you're reading half from each drive. However, that obviously means that if one of the drives fails, you've lost half of the data, and that's what it means by the redundancy. So RAID 5 uses at least three drives and strips data across multiple hard drives to improve performance via simultaneous data access, but unlike RAID 0, RAID 5 includes correction codes, so parity bits between the data. So it sounds like it's basically a combination of the two drives, although it's not mirroring the exact contents. It's basically providing the speed and performance benefits that you would see from a RAID 0 configuration without the same loss of redundancy. So it has greater fault tolerance. 1, 0, and 5 aren't the only RAID configurations. There are more, so let me just open up this other link. We can see we've got RAID 0, we've got RAID 1, we've got RAID 5, which is striping with parity, striping with double parity, and then combining mirroring and striping. But for everything we need to know here, we've covered it. So let's go and see how we can start trying to recover some of this data. So what happens when a hard disk fails in RAID 5 config? Because of parity information, all data available in one case of the disk fails. If extra spare disks are available, then reconstruction will begin immediately after the device failure. However, if two hard disks fail at the same time, all data are lost. In short, RAID 5 can survive one disk failure, but not two or more. And that's exactly what we've got. We've got one disk which is a lot smaller than the others and seems to be corrupted, but we've got two which appear to be working as expected. So how do we recover this third disk? Well, as I mentioned, there are some commercial solutions available. Some tools, I think Ncase has the possibility to actually reconstruct the RAID 5 systems, but we don't actually need that. There are some scripts out there as well. Let me open up another link which I found particularly useful for understanding how this works. So I thought this was a great explanation by Mustafa, and you can see here they've got a diagram. So here's the three hard disks, and then there's also the parity as well. And you can see here basically a data block A will be written to the disk if you have RAID 5 configuration with 4 disks. The data will be split into these 3 hard disks, and then there's also the parity. So that's going to improve performance because you've got 3 times the read and write possibilities. RAID 5 configuration also protects your data against disk loss, but does not copy every piece of data. So essentially what it's saying there, it's not like RAID 1 where it's mirroring all of the data. It's still splitting the data across disks to give you a performance boost, but it's also providing some protection, and it's doing that using the parity. So parity is a result of the XOR gate, and you can see in this example we've got A1, A2 and A3. Let's just say we've got a 4 bits of data that we want to store. We're storing that to A1, A2, A3. Here's an example of the XOR, so let's just explain how XORs work, and these are going to be XORed together. So we're going to XOR A1 and A2, and then the result of that is going to be XORed with A3, and the result of that is going to be 0, 1, 0, 1. In fact, let's go through this as well. Let's open up Sublime. Oh, let's move this over here. So we've got A1 1001, and we've got A2 which is 011. So an XOR on 1 and 0 is going to be 1, an XOR on 1 and 0 again is going to be 1, an XOR on 1 and 0 again is going to be 1, and an XOR on 1, 1 is going to be 0. So that's our result, and then the third one was A3, which is 1011. So we'll XOR those, and we'll get 1, 1 is 0, 1, 0 is 1, 1, 1 is 0, and 0, 1 is 1. So there's our result, the same as they got as well. So that's how the parity is calculated, and then that'll be written to disk as the parity. So how does that protect us from data loss? Let's say that we lost disk 2, so A2 is missing. All we've got is A1, which is here, A3, which was 1011, and then the parity. So we can basically XOR the 3 of those together to recover our A2, and that's just the reversible nature of XOR. So another very basic example is if we were encrypting some data. Let's say we've got 1100, that's our plain text, and then we've got our key, which is, let's say, 1010. So our ciphertext then would be to XOR that. So 1 and 1 would be 0, 1 0 would be 1, 0 and 1 would be 1, 0 0 would be 0. So that's our ciphertext, and we send that across. Then we keep our plain text, we send over the key through a secure channel and the ciphertext to somebody, and then they can now say, okay, I've got the key, I've got the ciphertext, so I'm going to XOR those. I'm going to see that the plain text is 1 1 0 0, and there's back to our original plain text. So it's a reversible operation, and that's still the case when there are when there's more than 3 elements. And essentially that's all we need to do then. We need to XOR the 2 working disks to recover our broken disk. So let's close this stuff down, and the first thing I'm going to do is rename some of these images. So let's call our first working image disk 1.image. Let's call our second working disk, disk2.image, and let's see what else we've got here. I don't think we need that broken image at all, but I'm just going to leave it there for now. Let's open up Codium, exploit.py, and I'm just going to paste this in. This is just a very basic PwnTools script that I put together. So we're going to read in our two disks, disk image 1, disk image 2, and we're going to XOR them, and then we're going to write the third disk to a file. So super basic. Let's run that and see what we get. Takes a little while to run, and there we go, we've got a disk 3 image. So we could do the same sort of thing again. Let's try and grep -i-a HackTheBox from disk 3, and again we see some HTTP in there, but it's not relevant. Let's try and do strings again, strings-n10 disk 3. Scroll through just to see, do we see anything recognizable? And we do. We can see EXIF tool is mentioned here. We can see what looks like some parts of a PDF, and we can see here image to PDF converter. And that's good because we saw a PDF file name previously. So we could again try and do something like foremost on disk 3. Does that produce anything? List output PDF. Okay, so it does. Let's go and have a look at it. Go into our output, PDF, open that up, and it actually looks a bit like stego. So sometimes with a steganography challenge you'll see some kind of mix of data in like an image, which is what it looks like at the moment. But it's obviously corrupted because although we have extracted all the disks now, we need to go and reconfigure the RAID 5. So let's do that. So we can use losetup. Let's do losetup-h, and we can get up the options here. This will set up and control loop devices. We can also use TLDR, which I quite like because it gives you just some quick examples of how to configure these things. And what we're actually going to do is something like this: sudo losetup and then dev loop, and then provide our image file. So let's do sudo losetup, and we'll do dev loop 1, and then we'll pass in our disk image 1, and that's our first one. Let's try and do the second one as well. All looking good. Let's do the third, and that was fine as well, no errors. And now we want to rebuild the RAID 5 array, which we can do with mdadm. Let's do mdadm-h. This is used for building, managing and monitoring Linux MD devices, aka RAID arrays. So again, we've got some options here. We can also use TLDR if you're in a hurry and you just can't be bothered even reading the help menu. Then this is always a good option. And essentially what we can do here, we need to provide the RAID level. So we know it's a RAID 5 config. We've got 3 hard disks, so we'll need to provide that. And that's pretty much it. Let's do mdadm and then create. Let's do level equals 5. Let's do RAID devices equals 3, and then dev md0 and dev loop 1, dev loop 2, and dev loop 3. Oh, we need to be sudo. Oh, I just realized I missed a slash. Was wondering what was going on there. Okay, so that has started, and now let's try to mount this. So dev md0, let's do mount RAID, and let's try and list what we've got in that RAID. There we go, yeah, so we've got our PDF. Let's take a copy of it and we'll copy that here. We'll go and open that up, and we'll see that it's unsupported. Okay, I had to do a little bit of troubleshooting there because this worked for me whenever I solved the challenge just before I recorded the video, and now it's not working. So it seems to be that the issue is the order of the disks. So I think we had disk 1 and disk 3 weren't corrupted, and we've had to restore disk 2, and that's not the way that I've done them here. So what I'm going to do, we'll just leave everything as it is, but I'm going to move disk 2 to temp. I'm going to move disk 3, which was the one that we produced with the XOR. I'm going to move that to disk 2 .image, and then I'll move temp to disk 3 .image. And let's just try this again. Let's do sudo losetup and then dev loop 1. We'll do that with disk image 1. Same again for disk image 2, and the same again for 3. And then let's rebuild the RAID array, so sudo mdadm create, and the level is 5. The number of devices, number of disks is 3, and then dev md0 and our 3 loops. Okay, I think that's looking good. Let's try that. Yep, that seems okay. Let's also, I'm going to do sudo make directory mount RAID, and then let's try to mount it dev md0 mount RAID. Okay, let's try and copy this again. Hopefully this time it's not going to be corrupted. We'll try to open it up, and yep, it's looking good. We've got a thumbnail. We open that up and we can see that we've got our flag right here. And that's going to wrap it up for this video. It's gone on a little bit longer than I expected, but hopefully you've learnt something along the way. I haven't seen this challenge before, so I thought it was pretty cool. And yeah, if you have any questions or comments, as ever, leave them down below. Thanks.